The geostrophic wind is said to blow parallel to straight isobars, like the one shown here. We will understand why this is so later on. But why do the isobars have to be straight? The reason is quite simple. If we have curved isobars, then another force is introduced, namely centrifugal force. You may have experienced it yourself when driving quickly round a sharp bend. You feel the sensation of being thrown outwards. This is the centrifugal force acting. So the moment we have curved isobars, the wind is no longer described as being geostrophic, because now there are three forces. In fact, it becomes what we call the gradient wind. We will discuss this wind later on, but for now, let us continue with the geostrophic wind. If we know the wind blows parallel to straight isobars, how do we know which way it blows along the isobars? In order to deduce this, we need to use Bayes-Ballott's law. He stated that with your back to the wind in the northern hemisphere, the low pressure will be on your left. Look at the diagram of a surface pressure chart and the values on the isobars. You will see that a low pressure must be to the west of the diagram, so pressure is decreasing in that direction. Therefore, using Bayes-Ballott's law, the wind must be blowing from the south to the north. That is, a southerly wind. In the southern hemisphere, the law is applied differently. This time, with your back to the wind, the low pressure is to your right. So, in this example, the wind will be blowing from the north to the south, a northerly wind. So to confirm the direction of the geostrophic wind, you must remember how Bayes-Ballott's law applies to both hemispheres. Having seen how to work out direction, let's now consider speed. In fact, we have already covered how to do this. If you remember, in order to calculate the speed, we took the spacing between isobars and used that spacing on the geostrophic wind scale to read off the speed. Remember to use the latitude on the geostrophic wind scale that corresponds to the latitude at which you took the isobar spacing. We have now learnt how to calculate the direction and speed of the geostrophic wind. But what we also need to know is at what height it blows. If you remember from the lesson on turbulence, there was a layer of air moving close to the surface that was disturbed and slowed due to the friction of the surface. This layer is called the friction layer. The reduction in speed within this layer is due to surface friction and not to any reduction in the pressure gradient force. But a reduced wind speed causes a reduced Coriolis force. The two forces of the geostrophic wind are not in balance anymore. Therefore, the geostrophic wind will only be found above the friction layer, or above the friction level. If you remember, the height of the friction level changes, depending on the time of day and the nature of the surface. Generally though, we can consider the friction layer to extend up to about 2,000 or 3,000 feet. It is above this that the geostrophic wind blows when we have straight and parallel isobars. The last point to make about the geostrophic wind is its relation to latitude. Looking at the velocity wind formulae, we can see that a decrease in latitude, theta, causes the term sine theta to decrease, which increases the velocity of wind if all other factors remain constant. So even though we may have a constant pressure gradient force, and therefore a constant isobar spacing, the velocity of the wind will increase with a decrease in latitude. Note though that for the geostrophic wind, this will only be true down to latitudes of 15 degrees, because between this latitude and the equator there is no Coriolis force, and so geostrophic winds do not blow. Let's look at an example. Here we can see the geostrophic wind scale. At 70 degrees north, with this isobar spacing, the velocity is about 25 knots. However, the same isobar spacing at 40 degrees north gives a speed of about 40 knots. This demonstrates the principle very well. The reason for this is very complicated indeed, and is related to the scale of the Earth on maps. It is not necessary to understand the reasoning behind this particular point, but knowledge of its effect is vital. Having considered all the essential facts about the geostrophic wind and its relevant forces, let's now bring all these concepts and ideas together to understand why the geostrophic wind blows parallel to the isobars. We will use an example of a high and low pressure suddenly being generated somewhere in the northern hemisphere. What is immediately apparent is the pull by the pressure gradient force on air, moving it towards the low. However, as the air starts to move, the Coriolis force kicks in. Remember, this acts at 90 degrees to the wind direction. Notice, though, that initially the Coriolis force is not very strong, because the wind is only just starting to be accelerated. The resultant flow of air will look like this, indicated by the blue line. Notice it is small in size, because the speed is still quite small. However, the process is not yet complete. In order for the wind to be geostrophic, the forces must be balanced. Let's see what happens next. In the next step, we still have pressure gradient force pulling towards the low pressure. But because the speed is increasing, the Coriolis force is a little stronger, and again acting at 90 degrees to the wind direction. The resultant wind in blue is now shown. Slowly you'll be able to see what happens. Again, if we take another step, we have the pressure gradient force pulling the air towards the low, and since the acceleration of wind is continuing, the Coriolis force will be greater, and acting at 90 degrees to the right of the direction. Now we have the final step. The pressure gradient force is acting towards the low, the Coriolis force is acting in the opposite direction and in balance to it, with the resultant wind now blowing parallel to the isobars, with the low pressure to the left, just as discussed. This is how the geostrophic wind is generated, and ties in all the facts we have learnt so far. The concept of the geostrophic wind is very useful to us. It can act as a benchmark to help understand other effects. Let's use the last step from the previous scene to understand what happens to wind within the friction layer. In other words, the surface winds. Looking at the image on the left, which shows the northern hemisphere, we can see the two forces opposing each other and in balance, with the Coriolis force acting at 90 degrees to the right. The geostrophic wind is the blue line pointing straight up. The image on the right is the geostrophic wind in the southern hemisphere. Notice the Coriolis force acting at 90 degrees to the left of the geostrophic wind. What we need to consider is what happens within the friction layer. Firstly, we know that the speed of the wind is reduced due to friction. Since the Coriolis force is proportional to speed, then if the speed reduces, so will the Coriolis force. Notice now that the forces are not balanced. The pressure gradient is now the stronger force, and within the friction layer will cause the wind to be deflected as shown. Replay this scene using the backward and forward buttons, but this time looking at the image on the right, which is for the southern hemisphere. Looking at the southern hemisphere image, we can see how the surface wind blows in relation to the geostrophic wind. It is said that in the southern hemisphere, the surface wind is veered and decreased from the geostrophic wind. Look at the image on the left for the northern hemisphere. Here the surface wind is backed and decreased with respect to the geostrophic wind. These are fundamental diagrams to remember. When using the diagrams, it is important to understand what is happening to speed and direction at the surface through to the friction level, where we find the geostrophic wind. As we climb from the surface in the northern hemisphere, the wind increases in strength and veers. It was only frictional interference that caused the surface winds to be different from the geostrophic. Therefore, it follows that different amounts of surface friction will cause different changes in the surface wind speed and direction. What we will look at now is how the nature of the surface, either rough or smooth, affects the speed and direction of the surface wind when compared to the geostrophic. The examples shown here are from the northern hemisphere. The image on the left will be used to understand surface winds over a rough surface, like a land mass. The image on the right will be used to understand surface winds over a smooth surface, like the sea. Let's concentrate on the image on the left. If the surface is very rough, then we would expect the surface wind to be much slower than normal. This means that the Coriolis force would be much smaller than normal. Remember, the Coriolis force is proportional to wind speed. As a result of the large imbalance of forces, the surface wind will be massively deflected from the geostrophic wind. In fact, this deflection can be quantified. The angular deflection is approximately 30 degrees, and the surface speed approximately 50% that of the geostrophic wind speed. Looking at the diagram on the right for a smooth surface, we would expect less friction and less of a reduction in the surface wind speed. So the Coriolis force will be reduced, but not as much as we saw for a rough surface like the land. The difference between the forces is not as much, and therefore the angular deflection much less. The surface wind is a lot closer to geostrophic than over the land. The angular change we see is a lot less than over land, only 10 degrees difference. The surface speed will be higher than over the rough surface. This time, the speed is approximately 70% of the geostrophic, as opposed to 50% over land. To observe analogous situations in the southern hemisphere, just click on the button to see the change.